Hi everyone, myself B. Praveena. I'm the Assistant Professor of Mathematics in Institute of Aeronautical Engineering College. Today I want to discuss about the topic on Cayley-Hamilton theorem and Cayley-Hamilton theorem statement and that related problems. Okay, first I'll discuss with the theorem statement. What is the statement of the Cayley-Hamilton theorem? Okay, that is every square matrix satisfies its own characteristic equation. Every square matrix satisfies its own characteristic equation. That means what? Here the square matrix satisfies its own. Okay, what is the form of the characteristic equation? Det A minus lambda I is equal to 0. Okay, but the given matrix satisfies its own characteristic equation, that is called as a Cayley-Hamilton theorem. We will discuss clearly on the first question, that is show that the matrix A is equal to 1 minus 2 1 1 minus 2 3 0 minus 1 2 satisfies its characteristic equation, hence find A inverse. Once observe, the given matrix is square matrix or rectangular matrix. This is square matrix and this is 3 by 3 matrix. We have to show that the matrix satisfies its characteristic equation, and from that we have to find A inverse value. Okay, then here what about the characteristic form? That is characteristic equation is det A minus lambda I is equal to 0. From that, what about the form of the det A minus lambda I? Det A minus lambda I is equal to 0 means A means 1 minus 2 1 1 minus 2 3 0 minus 1 2 minus lambda into 1 0 0 0 1 0 0 0 1. This is the matrix for the characteristic equation, that is A minus lambda I is equal to 0. After subtracting that, there is 1 minus lambda minus 2 1 1 minus 2 minus lambda 3 0 minus 1 and next minus 1 and 2 minus lambda is equal to 0. After multiplying with lambda and subtracting with the minus, then we get that matrix form 1 minus lambda minus 2 and there 1 1 minus 2 minus lambda 3 0 minus 1 2 minus lambda. Take the question here 2. There also 2. Okay. Then here, okay, from getting that characteristic matrix form, we have to, okay, find the determinant for that. How we are finding? Here I am applying the column operations. How we are getting that column operations there? I am using C2 tends to C2 plus 3 3. That means I have to change the values in what? Where? In that C2. With respect to, I have to change the values in C2 with respect to what? C3. Once observe here, what about the C2 column, that is minus 2 minus lambda minus 1 and 2 3 2 minus lambda. Okay, if you are adding these two, then directly here we get 0. That means 1 minus lambda, here minus 2 plus 2 0 and next element minus 2 minus lambda minus 3, that is plus 3. That means here we get 1 minus lambda and next one minus 1 plus 2 minus lambda, that is 2 minus 1 is 1 minus lambda, and the third column there is no changes, that is 2 3 2 minus lambda is equal to 0. If you are applying the column operation C2 with respect to C3 here, then the C2 directly it is equal to 0, that the first element as 0. Okay, and after that here I am taking 1 minus lambda common. Okay, in that second column I am directly taking 1 minus lambda common. After that we get 1 minus lambda 0 2 1 1 3 0 1 2 minus lambda is equal to 0. Okay, after that find the determinant directly. After the finding the determinant, here we get one equation form. What is that equation form? Lambda cube minus lambda square plus lambda minus 1 is equal to 0. Lambda cube minus lambda square plus lambda minus 1 is equal to 0. This is the characteristic equation from the characteristic matrix A that A minus lambda I is equal to 0. That is what? Lambda cube minus lambda square plus lambda minus 1 is equal to 0. Okay, that is the characteristic equation. This is characteristic equation. But Cayley-Hamilton theorem satisfies, states that, what states that? Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. Here what they are asking in the question, show that the matrix is satisfies its characteristic equation. That means what? Indirectly what they are asking, Cayley-Hamilton theorem, is the given matrix satisfies its Cayley-Hamilton theorem or not? We have to observe that after getting that characteristic equation through the Cayley-Hamilton theorem, I'll write it as that characteristic equation from the statement every square matrix satisfies its own characteristic equation. Every square matrix satisfies its own characteristic equation. That means what? From that characteristic equation, I'll write it as, in place of lambda, as a cube minus a square plus a minus I is equal to 0. A cube minus a square plus a minus I is equal to 0. If you are solving this, if it is equal to 0 means, then the given characteristic equation, that means given matrix is satisfies its own characteristic equation. For that, I'll take, what about the given matrix there? The given matrix is the given question, that is 1 minus 2 2, 1 minus 2 3, 0 minus 1 and 2. And a square is equal to what? How we are getting that a square here? Just multiply the two matrices of A. That means a square is equal to 1 minus 2 2, 1 minus 2 3, 0 minus 1 2 into 1 minus 2 2, 1 minus 2 3, 0 minus 1 2. Okay, just multiply these two matrices. Already we know that how we are multiplying that matrices here. First row with the first column and first row with the second column and first row with the third column. Similarly with second row with first and second and third, and similarly third row with first and second and third columns in the second matrices. Okay, for that we get directly this. Or else if you directly for finding a square, for the directly you can use that calculator, scientific calculators. From that calculators we get directly a square, a cube, whatever it is. If you want, then use that scientific calculators for multiplying of the matrices. For that, here I am multiplying that a square. For that a square here, just multiply the two. That is, I am using that first row with first column. That is 1 into 1 1, minus 2 into 1 minus 2 and plus 0. And similarly, and 1 minus 2 and plus 4 and minus 2. And next 2, 1 into 2 2, minus 6 and plus 4. From that, here once observe here, 1 minus 2 means what? Minus 1, and there minus 2 minus 2 minus 4 and plus 4, that is 0. And next 2 minus 6 minus plus 4, that is also 0. Okay, continuing like this, we get the second row and the third row. That's the multiplication of the matrices. We get here directly a square. Okay, from that, if you get that a square, from that we have to take a cube. What about a cube? A cube is equal to here, a cube is equal to a square into a. A cube is equal to a square into a. What about a square there? Minus 1, 0, 0, minus 1, 2, minus 1, 0, 1. Into, what about a? A means 1, minus 2, 2, 1, minus 2, 3, and 0, minus 1, 2. Okay, again multiply the 2. From that we get directly, what about a cube? Minus 1, 2, minus 2, minus 2, 2, minus 1, minus 1, 1 and 0. This is a cube. Or else directly from the calculators also we get the same values for the matrices, that is a square matrix and a cube matrix. Okay, from that, after getting that a square and a cube, what the characteristic equation by the Cayley-Hamilton? A cube minus a square plus a minus I is equal to 0. From that, substitute there. The a cube is this, substitute, and what about a square? This is a square plus a minus I. Here once observe, just adding these all, we get completely zero means the given matrix satisfies its own characteristic equation. From that minus 1, once observe how we are adding that, minus 1, minus into minus plus 1, and plus 1 minus 1. 1 is minus 1, and here minus into minus plus 1 cancel, and 1 minus 1. 1 minus 1 is 0. Directly we get here 0. And similarly add each and every element from the second element. 2 minus 0, 2, plus into minus 2, 2 minus 2, 0, and minus 0, that is 0. And next similarly minus 2 minus 0 plus 2, minus 2 plus 2, 0. Therefore, completely after adding that first row directly, that completely the first row as 0. Similarly add with the second row, first element minus 2, minus into minus plus 1, that is minus 2 plus 1, minus 1 plus 1, 0, and this is 0. There, 0. And next 2 minus into minus plus 1, 2 plus 1, that is 2 minus into minus plus 1, and minus 2 minus 1, that is 3 minus 3. This is 0. This is 0. Similarly, last element minus 1 plus 2, that is 1, and plus 3, and next one minus 1 minus 2 minus 3, and plus 3, and 0. This is 0. That is 0. Similarly, at the last row, minus 1 minus into minus plus 1, 0, and 0 plus 0, that is 0. And next 1 minus 0, minus 1, and next one 0. That means 1 minus 1 is 0. And next similarly at the last element in the third row, that is 0 minus 1 minus 1. Next plus 2 minus 1, 0 minus 1 plus 2, and minus 1. That means minus 2 plus 2 is 0. Therefore, all after adding that all values in the all matrices, then we get directly this is equal to 0. That means if you get completely 0 matrix means for the given matrix it satisfies its own characteristic equation. Therefore, the given matrix satisfies his Cayley-Hamilton theorem. Okay, that's the concept for the first. Okay, then what's the question? Show that the matrix satisfies its characteristic equation. Okay, therefore it satisfies. Therefore, from that hence we have to find A inverse. How we are finding A inverse? For that, what about the characteristic equation from the Cayley-Hamilton? A cube minus a square plus a minus I is equal to 0. From that, multiply both sides with A inverse. A cube minus a square plus a minus I is equal to 0. From that, both sides multiply with A inverse, that is a cube minus a square plus a minus I is equal to 0. A inverse into a cube is a square minus a plus this is I minus a inverse is equal to 0. From that a square minus a plus I is equal to a inverse. From that characteristic equation, both sides multiply with a inverse, we get directly here what is a inverse? A inverse is equal to a square minus a plus I is equal to, that is A inverse. A inverse. Now, already we know that in the given matrix, what is A square? This is A square matrix. And what about A? Given question as the A matrix. And I means here the given question is 3 by 3. So that we can take I as also 3 by 3 identity matrix. That is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. Just add these three. We get directly the matrix is minus 1, 2, minus 1, minus 1, minus 2, plus 1. That is minus 1. 0 plus 2. 0 plus 2. That is 2. And next one 0 minus 2 is minus 2. Next minus 1, minus 1, plus 0, that is minus 2. Similarly, we can add all elements that is equal to the required A inverse. Therefore, what about A inverse? Minus 1, 2, minus 2, minus 2, 2, minus 1, minus 1, 1, 0 as the A inverse matrix from the Cayley-Hamilton theorem. This is the answer for the first question by using Cayley-Hamilton theorem statement. Similarly, I'll explain one more question. Using Cayley-Hamilton theorem, find the inverse and a power 4 of the matrix. Find the inverse and a power 4 of the matrix. Here, what about the given matrix? Again, they are given 3 by 3 matrix, that is 7, 2, minus 2, minus 6, minus 1, 2, 6, 2, minus 1. For that, what about here? This is 3 by 3 matrix and this is the square matrix. Cayley-Hamilton theorem satisfies its own. Every square matrix satisfies its own characteristic equation. That means here the given question is the square matrix. From that, what about the characteristic equation there? Det A minus lambda I is equal to 0. For that, 7 minus lambda 2 minus 2 minus 6 minus 1 minus lambda 2, 6 2 minus 1 minus lambda is equal to 0. Again here, what is common there? I'll take from that. Directly we can do the determinant from that. Whatever you have to apply, either column or row operations, from that we get directly one characteristic equation form, that is lambda cube minus 5 lambda square plus 7 lambda minus 3 is equal to 0. Lambda cube minus 5 lambda square plus 7 lambda minus 3 is equal to 0. By Cayley-Hamilton theorem, we have from every, what about the Cayley-Hamilton theorem statement? Every square matrix satisfies its own characteristic equation. Through the statement here we get one characteristic equation form. There we have to substitute in place of lambda as a, that is a cube. In place of lambda I am substituting a cube minus 5a square plus 7a minus 3 is constant. You have to multiply with I is equal to 0. From that, multiply with A inverse, we get A inverse is equal to here. Okay. Here, what's the question? Only we have to find inverse and A power. After getting that characteristic equation by Cayley-Hamilton theorem, there both sides multiply with A inverse. Okay. Here I am multiplying with A inverse. From that, A inverse into A cube minus 5a square plus 7a minus 3i is equal to 0. From that I am multiplying with A inverse, that is A inverse into A cube is A square minus 5 into A plus 7 into I minus 3 into A inverse is equal to 0. From that, what about A inverse? A square minus 5A plus 7I is equal to 3 into A inverse. From that, A inverse is equal to what? 1 by 3 into A square minus 5A plus 7I. A inverse is equal to 1 by 3 into A square minus 5A plus 7I. Okay, from that, this is that. Okay, from that, what about A square? Already we discussed in the previous. Okay, again from here, what about the given matrix A? Again multiply with A square means what? Multiply A into A. From that we get directly 25, 8 minus 8 minus 24 minus 7, 8, 24, 8 minus 7. From that A square, again multiply A cube means already we get A square into A square into A. From that, what about A square? 25, 8 minus 8 minus 24 minus 7, 8, 24, 8 minus 7 into A matrix. What about A? Here the given matrix. Just multiply again with that 2, we get directly A cube. Or else, if you are taking a lot of time for multiplying of the matrix, from that we can use directly scientific calculators for multiplication of the matrices. For that we get directly A square, A cube and so on up to A power n. Okay, here we require only A square and A cube. For that we can apply apply scientific calculators also. Okay, from that here a square and a cube, just substitute. Okay, here what about A inverse? This is A inverse. There we have to substitute A square matrix and A matrix and 7 into I. What is I? I means identity matrix. Okay, what is I? That is identity matrix. That means here A inverse is equal to 1 by 3 into, what about A square? 25, 8 minus 8 minus 24 minus 7, 8, 24, 8 minus 7. Okay, minus 5 into, what about A matrix? 7, 2 minus 2, 7, 2 minus 2, minus 6 minus 1, 2, and the last row 6, 2 minus 1. 6, 2 minus 1 plus 7 into 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, if you are adding these all, directly we get and 1 by 3. And after adding these 3 and we dividing with 3. Okay, from that we get directly here, after adding these 3, 25 minus 35 plus 7, that is minus 3. Similarly, we have to add each and every element in every row with that corresponding elements of the second row and third row. For that we directly get minus 2 and 2. And next 6, 5 minus 2, and the last row minus 6 minus 2 and 5. Therefore, what about A inverse there? 1 by 3 into minus 3 minus 2, 2, 6, 5 minus 2 minus 6 minus 2 and 5. This is A inverse from the Cayley-Hamilton theorem. And what they are asking in that same question, they are asking with find A power 4. Again, by using Cayley-Hamilton theorem statement, here from the Cayley-Hamilton theorem statement, what about the characteristic equation? A cube minus 5a square plus 7a minus 3a. A cube minus 5a square plus 7a minus 3i is equal to 0. What about the second question in that? Okay, we have to find A power 4. That means multiply both sides with a. And they are also multiplied with a. From that, this is A power 4, a into 5 into a square into a cube plus 7 into a square minus 3 into a is equal to 0. From that, what about A power 4? A power 4 is equal to 5a cube minus 7a square plus 3a. This is A power 4. Here already we know that a cube from the last part and a square also there and a. Then we have to multiply 5 into, what about a cube here? A cube is 79, 26 minus 26. 79, 26 minus 26 and minus 78, 25, 25 minus 25 and 26. And the next row 78, 26, 78, 26, 25 minus 7 into, what about a square? 25, 8 minus 8 minus 24 minus 7 and 8. And the next row 24, 8 minus 7. 24, 8 minus 7 plus 3 into, what about A? The given matrix, that is 7, 2 minus 2. 7, 2, 7, 2 minus 2. And the next matrix minus 6 minus 1, 2. Minus 6 minus 1, 2. And the last row 6, 2 minus 1. Okay, if you are adding these three, okay, if you are adding these 3, 5 into 79 minus 7 into 25 plus 3 into 7. From that we get directly the first element as, okay, if you are multiplying, once observe there, 5 into multiplying the first matrix, from that we get this. And after that 7 into multiply the second matrix, we get this. And next plus 3 into multiply with the third matrix, that is this. After adding these three, that is 395 minus 175 plus 21, that is 241. And the next one 130 minus 56 plus 6, that is 80. Next one minus 80. And similarly minus 390 minus plus 168 minus 80. From that we get directly this. And similarly, we can add each and every element in the three rows in that the corresponding three matrices we get directly, we get A power 4. This is the required matrix for A power of 4. Okay, this is the concept for by using Cayley-Hamilton theorem. We have to proved A inverse and A power 4, and sometimes they are asking show that the given matrix satisfies its characteristic equation. That means what, we have to verify the given matrix satisfied or not, Cayley-Hamilton theorem. Okay, in the two questions that the given matrix satisfied Cayley-Hamilton theorem statements, and after that we are finding A inverse and A power 4. This is the concept of the Cayley-Hamilton theorem. Okay, next class we will discuss with some other topics in the second unit. Thank you. Thank you for all.
Like, share and subscribe. Hit the bell icon for more updates.